Good evening. I'd like to welcome those of you who are here and those on live stream for the 7th out of 10 Discover Alaska lectures. Tonight, Professor Bill Simpson is speaking from the UAF Chemistry and Biochem Department. Bill has been at UAF for over 22 decades and also works in the Geophysical Institute. He's an atmospheric chemist and will be speaking about indoor air quality in Alaska. After his presentation, there will be time for questions.
Is the audio working? Great. Let's see if can you see the pointer? So thanks for coming, everybody, and thanks for the introduction and the chance to tell about air quality in this lecture series. And as I was introduced, I'm Bill Simpson, and I'm from the Department of Chemistry and Biochemistry here at UAF and also with the Geophysical Institute. We've been working on indoor air quality here in Alaska for a while, outdoor air quality here in Alaska for a longer period of time. And really, it's the community involvement which brought us from looking at outdoor air quality to starting to ask questions about indoor air quality. Because a really common question we would get when we would say we were doing an air quality study is, well, I spend a lot of time inside in the winter. What's it like inside my house? And so this talk is going to be about that indoor air quality. And hopefully we'll have a good amount of time at the end, but if I'm unclear on something or you want to ask a question, just please flag me down and I'd be happy to answer it as we go. So I particularly wanted to thank the Alpaca team. We did a big air quality study that I'll tell you about called Alpaca, and Pete DiCarlo from Johns Hopkins University and Ellis Robinson are particularly big contributors to this talk. So I wanted to give a special shout out to them. And then our website for the study, was at the bottom right there, fairair.community.alaska.edu or .uaf.edu. And that'll be on the last slide too, so you can see that there. Okay, so I think everybody here knows that air quality in Alaska sometimes can be pretty bad, unfortunately. So I've got a couple pictures here that just remind us of that. I mean, a month ago, we were in this horrible air that we had. So wildfire smoke was just all around the area and really hard to breathe at that time. I was wearing my COVID mask to ride my bicycle to try and knock down the particles while going around. Of course, we also have wintertime air quality where we violate the Clean Air Act, unfortunately. This is a local pollution type situation, and very strong inversions hold that pollution down at ground level. So while it's less dramatic than the whole sky being blacked out, the air quality can be as bad in the wintertime as it is in the summertime. So these are things that we unfortunately have here. A lot of the time, though, we have some of the cleanest air that you'll ever see around here. So a lot of time we have really beautiful air. And those are nice times. We kind of have to figure out what to do about these times. I think most people here and many people around know that you can look at air quality around any area by using some of these small sensor networks. So I think people are familiar with this one, the Purple Air Network, and you can see a map of air quality around the area, anywhere around the world, actually. There are thousands and thousands of these sensors out there. And these are crowdsourced. People buy these and put them on their houses. And it's reporting the air quality. A lower number is cleaner air. And you can see that today, this morning, the air quality was generally good around Alaska. So nice low numbers, as we'll typically see in the summertime. Interestingly, a couple of these are circled with a black heavy circle, like these ones and like this one. Those black heavy circles indicate that that's an indoor air quality monitor. And the indoor air quality monitors often have different values from the outdoor ones. And I didn't really cherry pick this, but this one's interesting that this indoor monitor is the highest reading that you see in this. And so something's going on in that house maybe they're making toast or something is making a bunch of particles, and that leads to particles inside the house, and we want to understand that. So that's the topic of the talk today, indoor air quality. So I have to say a little bit about units, because some of the slides I'm going to show are going to be using different units for air quality. And we're talking about fine particulate matter in general when we're talking about air quality in Fairbanks, PM 2.5, or small particles that get deep into your lungs and can cause damage down there. And the air quality index translates between the original measurement, which is this, the number of micrograms of particles per cubic meter. Cubic meter is about this big. And you can make a measurement of the mass of particles in there by filtering that cubic meter, and you weigh the filter, see how much weight it gained, and that's the micrograms per cubic meter. We translate that to a scale that's universal for all pollution, where we take it that 50 is the value that is the annual EPA average. So you want to be below 50 to be in good air. And then 100 is typically the short-term pollution standard. So the 24-hour for PM 2.5 pollution standard. And if you're over 100, you're in violation. You're into what they call unhealthy for sensitive groups as a pollution level. And you generally want to spend every day under 100 and the year on average under 50 in order to be breathing clean air according to the EPA standards. So these are the numbers. I'm generally going to use AQI, and what was shown here was actually the air quality index. So AQI as the unit, and this house, their toast is not putting them into violation, but it is putting them higher than their annual average should be. Okay, so when we had this recent wildfire event, these are the AQI measurements that there were in Fairbanks. And so we're on the AQI scale, like I said, 100, you don't want to be above 100 for any 24-hour period. And we spent maybe almost a month, 3 weeks here, over 100 in the outdoor air quality. And everybody knows it was horrible air then. And what can we do about that? Can we go inside? How well do houses protect us from this? So that's one of the questions we're going to ask today. As I said, many times of the year, we're just down at baseline, very clean air around here when we're not under forest fire conditions in the summer. So the reason that the air quality index is defined, and the EPA defines this, is that mortality and other adverse health outcomes come from breathing bad air. So this is a very famous study, the 6 City Studies, which is almost 20 years old now. And in this study, they looked at the correlation between excess mortality and the fine particulate concentration. So this is the fine particulate concentration. 35 is 100 AQI, 12 is 50 AQI. And so this city, which I think is Portage, Wisconsin, was defined as the reference city here and has a relative mortality risk of 1. And so these other cities, which had higher particulate loadings on average, had higher mortality. And those are bad outcomes, and you don't want to be breathing that air. So based upon data like this is how we got the EPA standard of the annual average of 12 micrograms per cubic meter here. A thing that we can point out in this, which is actually also shown in subsequent studies, is that there's not really a threshold to this. There's not a level that you come down to, and then below that, you're in clean air and you're fine. In fact, as cities have cleaned up and has gone down, we see this continues to go down. So you really want to minimize your exposure to fine particulate matter as much as you can. We have not found an obvious threshold on this. And it's a good thing to keep yourself in clean air as often as you can, and particularly for indoor air, if you can do things to clean up your air, that can help you to get lower on this curve and have better health outcomes. So this is, again, an outdoor air study, but that's kind of the beginning of a lot of the indoor air work, is how things work outdoors. So with that introduction, when we think about these times when it's really bad outside, like summer wildfire events or during the winter when it's really cold and we're going to have our house closed up, we're inside a lot of the time. 95% of the time, probably in the winter, you're inside. And then at least when this wildfires were happening, I had the windows closed all the time. The place was as tight as I could to try and protect against these particles. So the things I want to ask today are, do houses protect us from bad air that's on the outside? How much do they stop infiltration of particles? Another one is, are there indoor sources that are going to make the indoor air bad? We've already seen one of those houses that had an indoor air sensor had bad air at one point. So what are sources that make indoor air bad? And then how can we clean indoor air? So those are my questions for today's talk. So there's been an active set of the atmospheric chemistry community, the research community that I'm involved with, that has been looking at indoor air. And indoor air is really complex because it's a mixture of lots of things. And those things can react with each other. So you can have chemical reactions indoors. And this has been a big topic in the last decade or so that we've really been working on. And the US National Academy of Sciences, when we come up with a big new question like this, often convenes an expert panel to talk about this. And they did, and then they wrote a report called Why Indoor Chemistry Matters. And if you just go to National Academy of Sciences, Why Indoor Chemistry Matters, you'll find this report. It's free to download, so you can look at it. It's quite long, it's hundreds of pages. But this kind of summary shows the complexity of what's inside of a house and what can affect the air quality inside the house. So they show a lot of things inside the house here. Some of these we've heard about for a while, like radon can seep up through your foundation and get into the house. When you're cooking, gases from the combustion, if you have a gas range, can get into the house. Personal care products and things you breathe out can lead to bad air quality. Personal care products, deodorants, perfumes, things like that. Chemicals from cleaning are an issue. Pollution from the outside getting inside. And then lots of things are made with chemicals in them that can outgas out of them. So computers, some plywood, engineered wood products, lots of things can put air, toxics and bad things into your air. Some of the things that can be quite important here in Fairbanks are things like mold and microbes. If you have a really tight house and it's humid in there, you can have problems with mold. You can have problems with wood stoves or combustion inside the house. So that can be an issue, and that's something we're going to talk about in the talk right here. And you can also have attached garages, which may have emission sources like carbon monoxide from cars, or you may be storing paints, solvents, pesticides, things like that in your basement or attached garages, which can get into the house. So comparison to outside air, there's a lot more that can be going on in your house, and there's a lot more variability in houses, how tight the house is, the particulars of the house. So there's a lot to study in terms of indoor air and trying to understand the chemistry. And this report kind of talks about key questions in that. So I said I would talk about the Alpaca study, and this is an air quality study that we just carried out here in Fairbanks in January and February 2022, so just a few months ago. And this was a large study. There were about 4 dozen people who came here to Fairbanks and another couple dozen who didn't come to Fairbanks but worked on modeling and other aspects of this from 20 institutions, both in the US and in Europe. And this study was trying to look at inversions, chemistry out in the cold and dark conditions, lots of things that you see down here. But what I want to talk about today is this part right here, which is that we wanted to study indoor air quality in response to the community asking the question, what's happening inside my house? So we rented a house, and We then looked at the air quality inside the house. We looked at outdoor air infiltrating into the house, and we looked at indoor sources like cooking and wood stoves. So that's a component of this big Alpaca study that just happened this last winter. We additionally, as a part of this project, are putting together a data meeting, which is coming up in a month, and a lot of data is going to be coming together, and we're going to be coming back to Fairbanks to talk about some more of the results. So look for that this winter if you're interested in the results of the study. So thinking about the house, what we did was we wanted to study the air inside the house. So we had an inlet for our sampling instruments inside the house. And then we had another inlet for our sampling instruments outside the house. And we're going to compare the air inside and outside of this house. One of the big questions is how much outside air gets inside, how much infiltration of the outside air to the inside occurs under kind of typical wintertime closed up conditions. This house didn't have a fancy ventilation system and HRV or anything like that. It was a fairly standard house in Hamilton Acres neighborhood here in Fairbanks. Another question that's really interesting for chemists is when we think about warming up things, often they turn into vapors. So they call that volatilization. And so a lot of the organic compounds that can be stuck to the particles might volatilize, might vaporize off the particles when you warm them up from -30 Fahrenheit outside to +70 inside. So that's a question we want to ask. How does the composition of the particles change when they come indoors? And then another one we wanted to ask is, what about things we do inside the house? So this house had a pellet stove that we used to see if there was some emissions into the house from this pellet stove. And then we also cooked some kind of reproducible, or we did reproducing the experiment, cooking the same chicken multiple times. So we did a few cooking experiments to try and understand what's going on with these sources. And then we did some mixed experiments to see how maybe particles produced by this might interact with particles that are produced by the pellet stove. So that's the idea of the study. We could only do this in one house. Houses are really variable, but we could only do it in one house because we needed to bring a lot of instrumentation to this. So there are in this garage hundreds of thousands of dollars of instruments to study the air. And 4 main universities brought these instruments to the house. University of Montana brought an instrument to look at organic gases. University of Washington at St. Louis brought a system that was looking at volatilization, so comparing what organics are on particles and are in the gas phase. University of Michigan had a system that looked at individual particles to see their chemical composition. And Johns Hopkins University had a couple instruments to look at gases and then also the aerosol particle composition. And all of these were real-time instruments reporting data at 5 minutes or faster. So really a state-of-the-art experiment put into this garage. And then we replaced the garage door with a garage door that we built, and we put an inlet through that garage door to sample outside air. And then we replaced the door to the house, which is back behind where this photo was taken, and an inlet went in there to sample the air out of the house. And we alternately sample the two to look at indoor and outdoor air. So that's a great study design to ask these questions. We want to, in the future, do more to look at more houses, look at multiple houses to see how multiple houses behave and see how some of the results that we saw in this house may be representative or not of other houses around the area. So the quick look results I'm going to show you here are coming from mostly the Johns Hopkins results on the particle composition and then the gases inside and outside the house. So the way we switched between those is we had a box that just switched between an indoor and an outdoor sampling, and it would just run 10 minutes of indoor air, 10 minutes of outdoor air, continually switch back and forth. And then we could monitor 2 spaces essentially in real time. So this is what the raw data looked like for a couple of gases. So carbon monoxide, people who've been here, a lot of people have been here longer than I have, but when I first got here, we violated the carbon monoxide standard because of largely cars, which were putting out carbon monoxide outside. Now it's much lower levels of carbon monoxide, but still there are some cars which are putting out spikes. So these spikes may be cars. They might also be wood stoves that can put out some carbon monoxide. But most of the spikes are in the outdoor data when the sawtooth kind of goes up here. And then the indoor data are always smoother because the air inside the house is more mixed by the fan system. This house was heated by a hot air furnace, and it was oil fired, and the fan was always on, mixing the air inside the house. So the air inside the house tended to follow behind what was going on outside. And then it was less variable than the air that was outside, particularly for carbon monoxide, which can have some pretty intense point sources. So if we split those data out, then we get two records. One of them is the, say, I'll look at the top here in the darker blue, that's the carbon monoxide outside, and then the blue is the carbon monoxide inside. And you can see that that air is infiltrating. We can get a time scale for the air to get in and out of this house, which for this house is something like an hour. So then the methane is following along like this. We can also do this for particles, and that's one of the big questions we wanted to ask here is how does the outdoor particle concentration compare to the indoor particle concentration? And this is the good part. If we have a talk here, the good, the bad, and the ugly, this is the good part of the talk here, which is that the air inside the house, the darker black here, is like a factor of 5 lower than the air outside the house. So this was in early February, in late January, early February. I don't know if you remember that, but there was a pretty stagnant period. The air got pretty bad, and we violated outside. You can see up to 150 micrograms per cubic meter outside, which is very, very bad air. So inside the house, it was generally about a factor of 5 better. So if you close up, and even in a not filtered house, you can have a significantly cleaner air inside. So that's the good part. Part of the bad part is when we did things inside the house, like cooking or running the pellet stove, we saw these spikes. So these were experiments we were doing, which we were running the pellet stove or running cooking vegetables or cooking, the chicken or pasta or various things we cooked there. And we would see pretty high levels of particles inside the house during those events. So that's something we need to think of. Those particles inside, we need to think about their health effects too. I mean, if you boil some pasta or something like that, you may make a lot of particles, but they might just be sodium chloride, or you might be cooking in oil and you may make some oil particles that may not be too toxic compared to pellet stove emissions tend to be fairly toxic. So we also need to understand the chemical composition, which we'll look at in a kind of brief view in a second. So one of the bad results is that we saw there was some leakage coming into this house from this pellet stove. It's something we'd like to see if it's a common thing that always that happens, or if it's something that was specific to this installation. But this is a study which is from Tony Ward's group at University of Montana, trying to understand how much better newer wood stoves are compared to older wood stoves. So he looked at PM in houses, PM 2.5 inside houses, and compared it to PM 2.5 outside of houses. And the black bars were measurements inside houses before they were changed out for a new wood stove. And then the white bars that are next to them are the same house, but after they've changed to a newer wood stove, and they've had a couple of weeks to get used to how to run it and fuel it and everything. It takes a little while to get used to it. So what they generally found is, well, in all these cases, the bars got shorter after the change to the new wood stove. So that's good that the air was cleaner inside these houses after they changed out the wood stove. But still, some of the houses have some pretty high particulate levels even after the change out. So sometimes you still can get some significant amounts of particles into the house. So we knew this. This was using wood stoves, not pellet stoves. So our study had a pellet stove in the house and saw that effect. And again, that's something we'd like to know how common that is, if that's a common thing, by working with the community to try and do further studies on that. So we see newer stoves are generally better, houses vary a lot, and there can be some emissions into the house from wood stoves. Okay, so here's some of our data again. So on the top, we have the outside PM concentration. And what we've now done is from that instrument, the Johns Hopkins instrument, they can break down the composition of those particles into different types of compounds. So organic compounds are compounds that have carbon, hydrogen, oxygen, and those compounds are shown in green here. Sulfate compounds are shown in red. The blue is nitrate, and then the chlorine compounds are shown in this, I don't know what you call that, magenta color, and then the orange there is ammonium. So you can see the composition of these particles. And in Fairbanks, we knew this from outside air, that organics are one of the most common species that we see there. And then we also have a fair amount of sulfates in our particles here, not too much of most of the other compounds. Inside the house, we can also look at that. And in general, when there's infiltration, like this was infiltrating in, again, it's down by about a factor of 5, but it looks like about the same composition. So it looks like the composition's fairly similar. We're going to be working on these data more to get more detail to see if there's some more subtle changes to this, but it looks like that's coming inside. When we did the experiments inside, you can see that these are more organic rich. There's much more green to these than the sulfates in these particles. So different composition. And as I said, we're going to want to be looking at trying to understand what those compounds are and how bad their health effects are. So again, this is showing those periods when the pellet stove was on and we were seeing these particle loadings and mostly organics, which is what you'd expect from a pellet stove because you're burning essentially organic materials in them. Okay, so to look at that question of the outdoor to indoor transit, what we've done here is looked at the sulfate concentration. Sulfate is a compound that we don't expect to come off of the particles. Once it sticks to the particles, it should just stay in the particles. So it's a good tracer of transport from the outside to the inside because it's not going to change once it comes inside. So here's looking at the sulfate outside. And then in this lower level, that's the sulfate inside the house. And we correlated them with a lag, and we found that there's an offset of about 40 minutes. That's the time scale for those particles to get into the house, roughly, the lag for them to get in. And then I don't know why, but this isn't showing these dots right here, but we made a correlation plot. So trust me, there are a bunch of dots here, and the best fit line is this slope right here, which indicated that 18% of the outdoor sulfate was seen in indoor particles. So again, it's something like a factor of 5 reduction in the particles inside this house, which I think is a great result and nice to know that you're breathing a lot cleaner air inside when even just a house is simply closed up.
Before you move that location,
yeah, so indoor. Yeah, unfortunately, I don't know why the color didn't come out very different. In mine, these were different colors of reds. And so let me point to it, that this lower one is the indoor and the upper one is the outdoor. But yeah, this slide somehow didn't come across well at all. Sorry about that. Okay, so then looking at the composition, these are just the average compositions that we have, and looking with no experiment, we see that the composition outside and inside the fractional amounts of organic sulfate in each of the others looks to be about the same indoors and outdoors here, but again, a factor of 5 reduction. When we switch over to doing an indoor experiment, cooking or pellet stove, what we find is that the indoor air quality becomes worse, higher concentration, and most of that new stuff is organic materials. So we need to now do some studies on what these organic materials are, and we can use the data we're getting to look at individual chemicals. Additionally, a couple groups were here, one from University of Irvine, which is going to measure the toxicity of the particles, and also a group from Georgia Tech. And they're going to be looking at the toxicity and the production of organic reactive oxygen species from these particles indoors to try and get a feel for how bad these are. We can also look at that as a diurnal cycle to see what it is, and we see typical diurnal cycles outside, a lot more variability, and then it's kind of smoothed out when you go inside to this house. So to connect it to health, one of the ways we can do this is by looking at the chemicals and the mass spectrum. So in this experiment, we have a first period of time out to here, which was before starting an indoor experiment. We called this a mixed experiment, one where we did a pellet stove burn, and then we cooked at the same time the pellet stove was on to see the interactions of those particles. And you can see the particle loading goes up during that time, and then we turned it all off and things decayed back to background levels. And so we then looked at the mass spectrum. These are which compounds are there, and they're colored in the same way. I'm sorry, the colors will be there when I got it right here. So you can see the organic species are in green, the nitrate species is in blue. So each of the species is shown there. And you can see that the composition is really quite different during the outdoor air infiltrating in and during the pellet stove burn, where there's much more of these organic species. And we're trying to trace down what exact compounds these are to get an idea for their toxicity. And then when they start to mix and react with each other, then we get into this situation. And that's one of the things we want to understand. Okay, so I wanted to shift gears for a second here to point out something. This community has so much knowledge about air quality and how to deal with this situation. This was a letter to the editor from a 50-year resident. And this person wrote in saying that if you have a forced air furnace and you're using the furnace filter to clean your indoor air, then why don't you change that filter? Because it probably hasn't been changed in a while. And he said his wasn't changed for a while and it was pretty dirty. So I thought that was a great idea and got nice comments of people saying that this is a great idea and thank you. And so there's a lot of knowledge out here. So we actually did this experiment, changing the filter in the house. And we were working with the Cold Climate Housing Research Center to work on the ventilation of the building. And they recommended that the house was running a MERV 4 filter. MERV is a rating of how good the filter is. A MERV 4 filter, I think, we would hear is not a good filter. You can see through it. It's kind of a cat hair catcher filter, not much of a filter at all. We couldn't change it to a really good filter, like a MERV 11 or a 13, which is what you would want to do to really get clean air in your house, because this furnace was pretty old and CCHRC said the fan couldn't handle it. But we did try switching to a MERV 8 filter, which is kind of a moderate pollution blocking filter. And unfortunately, we didn't find that that filter cleaned up the air much inside. So these are looking at plots of showing that the middle line is the median value. And there's not much difference between having the MERV 4 or MERV 8 filter in this indoor-outdoor ratio. So I said it's about 0.2, 1/5 on average. And so we couldn't really clean up the air much inside this house with the filter change. But if you wanted to do this yourself, you could work with HRV people or HVAC people to figure out what filter you could put in there. And you may be able to put in a filter that would have more effect than this MERV 8 filter had. Speaking of filters, you may have a HRV system in your house. So this is actually the filter from my HRV, which is a MERV 8 filter. And you can see it caught a lot of this smoke. This was just loaded up during these most recent wildfire events. I would often put it on to recirculate to let this clean the air in the house. And I found that using that and an air filter, I could get from the outdoor air, which was almost always over 150 to 50 or so in the house, under 100 or often under 50 inside the house. So you really can clean up the air inside your house. You can use one of these. This is the air purifier I have, and you can see this filter was originally white, but you can see it's all loaded up with particles. I think if anybody has one of these and you look at your filter, you'll see it's all loaded up. And I wanted to point out, you don't have to buy a fancy one of these things. You can also make one of these, they call them Coursy Boxes, or Rich Coursy is the person who first made one of these. You essentially take some MERV 11 or 13 filters that you get, 28-inch filters, you tape them together. Here, the kid did some nice duct tape work with some nice colored duct tape, and put 4 of those together and a box fan on top, tape it all together, and then you run this thing and it can really clean the air inside your house. So you can make a nice filter. It's pretty inexpensive to make one of these things. And I think he had a lot of fun making it. So overall, that's what I've had for you from our study. As I said, many groups worked in the house here, and we're going to have lots more results coming. So this is kind of a first stab at what we've got here. This is another picture of members of the team. So this is a lot of the people at the end of the study. And I can point out Ellis Robinson right here. This guy right here is Ellis, who did a lot of the measurements here. And Pete DiCarlo wasn't here at the time of this photo. Some people had already gone home at this time. So that's what I have for you today. I'd love it if you got in contact with me. You can write me an email. You can find me through the chemistry department. Love to answer questions now, but also you can get things from the Fair Air website, which you can get, you can find if you just type in Fair Air or Air Quality Fairbanks or something like that. So thank you very much. It was an electric stove, so it wasn't putting in a bunch of particles by the combustion, although that can happen, and you are putting in a lot of gases also to a house when you have a gas stove. But so it was an electric kind of a, not an induction, but just the ceramic top. We soon after trying a few experiments kind of settled in on the cooking chicken experiment. And the cooking chicken experiment did make a lot of particles. They seem to be kind of oily particles, but that's what we're going to be looking at, is the composition of those particles. Again, we regulate air with something we can measure pretty well, the amount, the concentration in mass. But we know that not all compounds are equally toxic in mass. You know, I mean, I could eat a lot of sugar, but if I ate a lot of some carcinogen, I would have a lot worse outcome. So we really need to know what chemicals are in those particles, in addition to knowing there's a high particle loading. So that's something we're working on, and the whole community is working on, is trying to understand that.
Why didn't you use bacon?
We should have used bacon, probably. Yeah, I don't know.
The reason I asked that is I recently bought one of those Air Doctor air cleaners, and has an indicator on the front, blue light with a red light, terrible air, orange light, and automatically.
Right.
Well, my wife put 2 statements, but the range was almost red.
Yeah.
Several minutes until it cleaned up.
Yeah. Yeah. So far away.
30 feet away.
Yep. Yeah, you really do put a pretty tremendous load. I actually am reminded that people online can't hear the question, so I'm going to try and summarize it. The question was really why didn't we cook bacon? And bacon can lead to a lot of particles. Toast can lead to a lot of particles. These are kind of classic experiments you can do in a house to see a lot of particles. And he had a air filter like this one, mine doesn't change its level based upon the particle loading, but many of them do. They have a sensor in them, and the sensors say when the air is bad, and then they'll turn up the fan, essentially, go faster to filter the air. And yeah, it's pretty tremendous how high the loading can be in a house from cooking bacon, cooking toast, and things like that. But again, we need to really look at the composition of those particles to figure out. Probably bacon, because it gets pretty browned, has some polycyclic aromatics and some bad compounds in it. Some of these things may not be as toxic. So it's something we really need to look at in greater detail to try and figure out the effect of those. Having said that, you mentioned that having the range hood on, and it is a really good idea to have a range hood on while you're cooking and trying to get rid of that stuff that you're cooking and just get the particles where they're at their source and try and throw them out of the house. So, yeah.
A long time ago, Japanese difference and high into stomach cancer and I have and an observation was made. Japanese houses cooking and they did go on and they break down the protein and aldehydes.
Yeah.
That might be.
Yeah.
Organic breakdown. Exactly.
Yes. So yeah. So the question was about saying that there was a finding in Japan and Hawaii of high incidence of cancers, and they eventually related this to cooking in houses and aldehydes, reactive compounds. So.
Colon cancer, like again, diet.
Yeah. Yeah. So we can look at a lot of aldehydes in the VOC measurements. The instrument that we had was able to measure many aldehydes, and so that's definitely something we can look at. And filters were taken out of the house during the experiments and during other conditions, and those were brought back to laboratories where they've done studies of toxicity. So there's a number of assays of toxicity that they were doing, and also looking for persistent free radicals, which can be produced in these processes, EPR spectroscopy, which I know you know that. So there's a lot that can be done on that direction that we're trying to do to try to assess the toxicity and the broader community. One thing about indoor air is that probably cooking inside a house in Fairbanks and cooking inside a house in Hawaii or other places might be fairly similar if you're doing the same cooking experiment. So we wanted to a bit focus on interactions between outside particles coming in, indoor sources that are specific to cold places like wood stoves, pellet stoves, and interactions between a few cooking types and those particles to try and see the interactions there. So that was kind of our study design.
Yeah, Dr. Henley says it's not so much the PM 2.5, it's what's coating it. In I think it was 1906 fire in Fairbanks, whether it's anecdotal, I'm not sure. But they were running out of wood for the engines to pump the water, and they threw a bunch of pig carcasses in there with the grease, and that boosted back up. They put out the fire. So with the bacon, it's probably the grease that's doing it. I tried one PM 2.5, didn't work, and then I bought an Eco Wet, and I'm hoping you'll come up with some better one. And I ended up giving it away in Peru and buying another one. Cost about $100, and it's good. So I know. Got up to 671 a few weeks ago.
Yeah.
It's usually about like these guys, 3 or 4, something like that.
Yeah.
I put it outside in the summer, inside during the winter.
Yeah.
If I burn toast on the inside, it goes crazy.
Yep. Yeah.
And toast seems to be the thing. Do you recommend an affordable? It's one thing looking at the purple air, but I want to know. We're talking about internal, and I guess most of the internal comes from external. So that begs a different question, but if you could recommend and get a discount. Everybody should have some kind of, it's what we breathe.
Yep.
Inside or outside, depending on the season, to test what. Your Alpaca study, this is in progress, but you haven't got the results yet. So can we sign up and get emailed results afterwards?
Yeah, sure. You can write to me, or you can also sign up on the Fair Air. Unfortunately, this bar is over, but faired@community.uaf.edu. I think it's on my very first slide, so I'm going to get back to that. But yeah, so one of the things we did, which was really neat in this study, is we worked with the Tanana Middle School. So it's at the bottom here. We worked with the students at Tanana Middle School to build some small sensors. So this is actually a little sensor that the students at Tanana Middle School built. We built 75 of these, and we have plans for them, and we're going to put that onto the Fair Air website. So you could build one of these. It costs about $25 for the things that go into this. It's essentially the same as the Purple Air outdoor sensor here. And then it just reads out the AQI and the time. And so currently in here, the AQI is 0. I mean, with this wind that we've got now, you know, it's really a lot of air moving around outside. And as I said earlier, the air exchanges in these new buildings, particularly buildings with laboratories, tend to have a lot of air exchanges. So the air is pretty clean in here. So I can just pass this around. You can take a look at this little sensor.
What do you call it?
We call it the Tanana Air Quality Sensor for the Tanana Middle School, and it's printed in Tanana orange color. So if anybody's a Tanana graduate, it just reads out, it says AQI, and then it currently says 0, but it does see particles. If you make toast, it'll show you that. Yeah, so we can give you the information on the website there. Yeah. Yeah.
The concentration for air, so the outdoor air.
So it looks like, yeah, so most of the time at the house, it looked like the infiltration. I mean, of course, this whole time the house was closed up as tight as it could be because it was cold, as we would normally be in the winter. So no windows were open or anything like that. And we typically got this ratio of about 1/5 of the concentration that was inside the house. And so I think that's probably a pretty realistic number. There was actually a really neat study done in California during wildfires where they looked at the indoor air quality and outdoor air quality using indoor and outdoor purple air sensors. And they also got this number of about 1/5. Some have argued that that number may be a bit off because the people who buy a Purple Air indoor air quality sensor are probably more interested in air quality, may have more money to buy filters or things like that to clean up their house. But anyway, something like that is what you would typically see without any activities in the house. And then really the activities in the house are the things that can dominate what's going on in the house: cooking, wood stoves. And then we didn't do too many experiments, and we didn't actually stay in the house overnight because we didn't want too many perturbations to the house in this study confounding other things that we wanted to do.
I think you were looking at one house there
It was just one house.
that had forced air heat.
It had forced air, yep.
And both homes in Fairbanks that
Yep.
the last 40 years have not been forced air.
Yep.
So when you have a boiler, you don't have that potential to positively pressure the house. So you're keeping outside out, but you're also pushing whatever's in your air wall cavity.
Yeah.
I think there are times when it's much worse inside than outside. You have a leaky house where your house is literally a pump fucking on the ground, right on.
Right.
And gases and
Yeah.
whatever else is in the ground.
Yeah.
So you got to look at a lot more than one house.
Yep.
So
Yep. So the study design here really was to try to look at chemical changes to the particles on warming inside, one of the questions that I talked about, and look at how the particles change when they come inside the house. But you're exactly right that we do need to look at significantly more houses. We can't look at them in this great chemical detail, but we have ideas of how we can do simpler measurements in more houses. And that's exactly what we'd like to do, is to try to go out to more houses. And you're exactly right. I mean, also the way that the forced air system is balanced, you know, they may not have balanced correctly and the whole house may be slightly overpressured, slightly underpressured. There's a lot of things that can happen in houses that are, everyone's kind of a different experiment. And I do like these small sensors for that point of view, is that, I mean, you can do studies. I'd actually really like to, with the students, build more of these, and then maybe we can put them into a library. Maybe we can put them into places like that, that somebody could check it out and they could just do a little study themselves. West Valley High School, the chemistry teacher there, did a really nice set of studies using small sensors like this. So I think there's a lot that can be done. And I'm really glad people are curious about this. And I think you can figure out how your house is behaving and clean it up, hopefully, and hopefully without too much cost. But I think that all the studies that looked at health really indicate that the fewer particles you breathe, the better off you are, almost down to any level. So it's a good thing to try and protect yourself from particles. Yeah, so typically in the summer in Fairbanks, the area is pretty clean in general around here. There's a lot more vertical mixing. So one of the things we did in the study, which I didn't tell about today, but we looked at how high the pollution gets, and it's incredibly shallow how high the pollution gets in the winter, because there's not the sun coming down and heating the air near the ground and overturning it like there is now. So right now, the air is mixing vertically through maybe 1,000 meters, a kilometer. And in the winter, it's only mixing through 100 or 50. So it's not getting up as much, and that really traps it down near the ground, unfortunately. The other thing that happens is now it's windy, and that wind pushes the pollution out. In the winter, of course, when it gets really strongly inverted, you know what it's like downtown. The air's not going anywhere. It's just staying there. And you're stewing in that same air, and the pollutants that are getting put in just stay there, unfortunately. Yes, so yeah, traffic and home heating. I mean, home heating is probably a bigger contributor than traffic in most of downtown. We picked Hamilton Acres here to be an average between the downtown part of Fairbanks, which is kind of traffic dominated. So we had a site at the CTC building downtown, 604 Barnett, which is very near where there used to be a CO monitor when we violated carbon monoxide standards, and where traffic is high. And then we wanted to be outside of that in more a residential neighborhood, which is why we went for Hamilton Acres. Oh, yeah.
I heard somewhere once that PM2.5 particles. I know this is not your area. I couldn't verify that anywhere.
I don't really know.
Sounded rather ominous.
Yeah. Yeah, I don't really know how your body, I think it must somehow eventually get rid of them, but the PM2.5 particles, the smaller particles get deeper into your lungs, essentially. The big particles, you know, your little hairs in there and mucus is meant to stop this stuff. So the big particles don't get as deeply in there. And then the very fine particles can actually then even go through and go into your bloodstream and even cross the blood-brain barrier. So there's a lot of worry of these really fine particles getting deep into your body. I mean, there must be some way that your body cleans these things out eventually. But it's not my field, so you're right.
One of the things last year said that
Mhm.
once it's in your bloodstream, it doesn't get out.
Yeah,
It's there forever.
yeah, yeah,
That's all I remember.
right.
Of that topic.
Yeah. Yeah.
That sounds like that's something I want to answer. I talked to Kathy Cahill a few times, the drone screener, which I'm
Yep.
sure you're familiar with. You know well. And I asked her kind of the same questions. At some point, once they start delivering pizzas, is it possible to fly a drone over people, over the city? And there are good air qualities there, whatever I forget. Recently, I walked one around the library a few years ago, and it changes color every few meters,
Mhm.
depending on what the pollution is. So this is, in effect, house individual pollution, although my PM 2.5 meter tells me that 95% of the junk we breathe is wildfires in the summer.
Mhm.
That's where we go. But if we could fly, in effect, mow the lawn at whatever altitude, it depends on the rest of the season, and find out where the pollution is coming from. And what I suspect is, and I could easily be wrong, I often am, that the pollution is, we just say, oh, it's because Jose is, got a wood burner. We got five major power plants are coal.
Mhm.
And that's an exception anymore, unless Chinese. And what I suspect is once you do a high resolution with drones
Mhm.
over the city, and of course, it depends on wind time and everything else, and plug in the algorithms, you're gonna find out more of this than the powers that be want to admit is from the coal plants.
Mhm.
And that and the wildfires are what puts us in the grave a few years in, I think.
Yeah.
But you need to.
Yeah. So the question had to do with kind of what's the relative contribution of, say, coal-fired power plants or the power plants and wildfire to adverse health effects. And yeah, it's an important question, and it is one that we're trying to address in this study overall. And our study design didn't use drones. We would have loved to have worked with Kathy to use drones to do this, but it's hard to fly drones over the city and things, and getting permission in a city is difficult. So we weren't able to do that, but we used a tethered balloon, which we could raise up and down to look at pollution as a function of altitude. And then we also used a remote sensing method where we shined a searchlight essentially across to Birch Hill, and we had reflectors up Birch Hill. So the searchlight would look at different reflectors up and down the hill, and in that way section out the atmosphere to look at how high the pollution gets. And what we generally saw is that the pollution was largely trapped down near the ground when there are strong inversions. And then every once in a while we would catch a plume that was aloft, and at least during strong inversions, that tended to stay aloft because it was emitted from a tall stack and it was warm, so it rose up a little bit. And it didn't tend to come down on the scale of Fairbanks air shed, the local area here. So we're going to try to model that situation with models to try and understand whether that really did get stuck up aloft, and then how much of that may go out and then come back, or things like that. So we're trying to understand the exact question that you asked there, how much role there is. But at least the first looked like that most of the stuff we were seeing at ground level was emitted at ground level, at least where we were, so, and towards Birch Hill, other directions in town. I mean, that pollution from the power plants is definitely coming down in the interior, somewhere around here. But is it causing us to violate in Fairbanks is one of the questions that we would like to ask there. And then in terms of summertime, yeah, summertime particles are really bad, and we don't want to be breathing those. And I'm riding my bike with a N95 to try to really knock it down and staying indoors. So I think that's smart to do. But in terms of regulation, those are normally considered not controllable. So the regulations don't tend to apply to the summer situations because they're wildfire events. So it's not that nobody cares about the health effects. We all care about the health effects of that summertime pollution. And it is really bad air quality in the summer. And I definitely say protect yourself from it. But it's a different regulatory question than the wintertime question. Having said all this about the regulation, our study is really about science, trying to understand what's going on here, and we feed those results to regulators who deal with that. That's not our direct job here. Hope that was a good answer to your question there. And it is an important one we want to get at. I think we might be at time here. I don't want to take people longer than 8 o'clock. I'm happy to stay as long as you want to, but don't want to keep anybody if they have something to go to.
Just to make the point, that's interesting, that regulatory doesn't count when that's most of our pollution, something like that. Because I've spent years in Lima, Peru, and years in Cusco, Peru, I'm well aware that Cusco, Peru, at 11,000 feet, has much worse pollution than Fairbanks does, unless the fires are burning and we have an inversion, and then we're off the chart. So I talked to 4 different countries' councils and the U.S. ambassador about this. And I finally traced down the guy at the university who's doing all the work, and I'm going on with him. But you see a lot of tourists in Cusco. You don't see me as wide here because you're going to have a stroke or a heart attack if you try to breathe. And so the U.S. ambassador said, well, my job is to protect American citizens. I said, the most dangerous thing they can do in Cusco is breathe.
Right.
And I'll say the same thing here. If it's the wildfires, whether or not it's regulatory, it's going to kill us. So they talked to Richard Music about somebody, what can we put in the window to save us from the worst, the 99% of the pollution? How do all of us put one of these in our front room?
Yeah, I agree with you completely. And I mean, the home filters are, I really think, a great way to knock down the pollution inside your house. You know, those Coursy cubes can really clean up the air. The other thing is there's been lots of studies about relation between COVID and fine particulate pollution and how much you can clean up COVID particles. So, you know, if you're indoors, you're breathing air that other people have breathed out. If you have a filter that can take out those small COVID particles, that can be a way you can protect yourself. There was one study that I was reading recently where in the bedroom of somebody, a family member had caught COVID. The rest of the family hadn't yet caught it. And they isolated the one person in a bedroom and put them in with an air filter or with an air filter with no filter in it as a placebo, essentially. And they found that you were able to remove COVID particles through one of these good air filters, and it was less likely that the other people in the house got COVID when this person was there. So you can improve the situation for many things through filtering of air. In general, I have not really eaten inside since COVID because, you know, it's bad. And that people close together taking in particles is a bad risk thing. So I think you generally, in most places, would want to eat outside and have a lot of air exchange. In the winter in Fairbanks, it's just not realistic to have all your windows open when some people are over. And I think filters are a potential way to go, but it's still, you need them to be pretty actively blowing to really take out a lot of particles. I should say in that study in the bedroom, they didn't have it on very high because people couldn't sleep. If you turn these things on high, you can't sleep. They really get pretty loud. How loud does yours get when it kicks in the air cleaner? How loud does the air cleaner get when yours automatically kicks in? Oh, it's still quiet. Good. Doctor, ear doctor.
That's one word with a capital Z.
Do you look at mold at all?
We didn't. So yeah, we didn't actually in this study. It was really more looking at the particles, and the house wasn't terribly humid. It was actually quite dry inside the house. So I don't expect that it was a problem, but it wasn't part of our study design. Yeah, the house was like 15% humidity or something, because we weren't occupying it. So nobody was taking a shower, we did these experimental cooks, but we didn't generally cook in there. So it was dry.
Thank you.
We want to thank everyone for coming and all your good questions. And be reminded that next week on Wednesday will be the 8th session. So unfortunately, I don't know the topic, but check out the paper or the online spot at UAF and hope to see you next week. Thank you. And thank you, of course, to Bill.
Hey, how you doing?
Nice to see you, sir.
Yeah, nice to see you.
You definitely didn't.